everybody, this is Mrs. Ewald signing in, and today we're going to go ahead and talk about error analysis. Don't blame it on human error. Keep that in mind when you're writing up your lab conclusions. We are going to be kind of doing a continuation from the measurement podcast that I already did, talking about precision when we're talking about a measurement, and we're going to be talking about accuracy, precision, and different types of error for you to use or to be able to explain when writing up a lab report. And Miss Heaton did an awesome job explaining sig figs, and this again kind of helps to explain why it is we are using significant figures so much in chemistry. So let's get ready. Let's go ahead and get started. Let's first talk about accuracy versus precision. Accuracy is the closeness of a measurement to the accepted value. So big thing here, you need to have an accepted value to measure it against. And for example, let's say you have three, concentrations of a solution. So 1.74 molar, 1.73 molar, and 1.75 molar. These three measurements are very close to each other. But in order for me to figure out if they are accurate, I need to be able to know what the accepted value is. So if I told you that the accepted value is 2.32 molar, that's what I want to measure it against. Obviously, I have really, really poor accuracy when measuring those three concentrations of a solution. So this would give you an example then of something that would be not accurate. And then you would have to think about, well, why is it that I have such poor accuracy? Precision, on the other hand, is the closest of a set of measurements to one another. So going back to this example, 1.74, 1.73, and 1.75, that is pretty darn precise because they are very close to each other, plus or minus 0.01 molar. A good example of something that would be not precise then would be having all varying different concentrations, like 2.87 molar, 1.48 molar, and maybe 2.61 molar. They're all very different from each other. And so this would be very poor precision. Now, obviously, when you do a lab, you're always going to want to have very good accuracy while also being very precise. It has a lot to do with the reliability of your data. This is a quote that I found and I thought was awesome, and that is that accuracy is telling the truth, precision is telling the same story over and over again. That should hopefully help you to remember the difference between accuracy and precision. Here's another analogy, and let's go ahead and do some examples then, telling if it's accurate or precise. A dartboard is a great way of showing because you have a goal here, right? You have your point where you want to be able to get it in, which is your bullseye. And so in letter A, we have all three darts making it into that bullseye. So this would have a very high accuracy. And this would also be very precise. So it's both, because you have all three of them in the same area while also being at your target. Looking at letter B, you have all three of them making it into the bullseye, so this would be high accuracy, if I'm spelling this correctly. However, they're in all different areas of that bullseye, so they're not very, very close together. So this would have less precision. Looking at letter C, based on where our bullseye is and where our darts are, this would be low accuracy. However, it's very high precision. If you could read my writing, sorry. And then in letter D, all of them are very far away from each other and far from the bullseye. So this would have to be low accuracy, well, while also having low precision. I don't know what I did with my C there. Sorry. We are going to be looking at more of these examples tomorrow in class when we work in class on everything from our podcasts. Now, percent error. This is a way for us to actually calculate. So you always want to have something quantifiable, meaning that we are going to have a number to say how accurate we are. So this is a number that tells us the accuracy of our measurements. So that is the purpose of it. And we're always going to want to make sure we calculate percent error whenever we are doing an experiment that has an accepted value, and we're going to compare that accepted value with the experimental. So this is what you get in class, in the lab. And the accepted value is the published value, or what your teacher would provide to you. So the percent error is the accepted minus the experimental over the accepted value. The accepted minus experimental, you just take the absolute value of that, so you're always going to have a positive number. You're not going to have any negative percent errors. And so here's an example. If you measure the area of this $100 bill to be 97.7 centimeters squared, but the U.S. Mint says that the area of each $100 bill is 96.3 centimeters squared, what is the percent error of your measurement? So you would take these two values and recognize what is the accepted, what is the experimental. So if you measured the area of this 2B, this is going to be the experimental, and this is going to be the accepted. You're just basically going to plug and chug these into that equation. So I would then take 96.3 minus my experimental of 97.7 and put that over my accepted again of 96.3. Take the absolute value of that for that subtraction and then multiply by 100 to get your answer. And I don't have my calculator with me, however. But what I would do right now is go ahead and plug and chug that into your calculator and see what percentage you get. Make sure that it is reasonable. I lost my money. And then see how accurate was your measurement. So obviously you want to have a very high, you want to have low percent error. The higher it gets, the further you are away from your actual measurement. So go ahead and do that calculation and then have that in your notes then when we check them. All right, systematic versus random error. In the beginning of this, I mentioned how you should never ever explain something as human error because it's not reliable, and quite frankly, you shouldn't be making mistakes and know about it and then write about it. So you should always mention two different types of error in a way of explaining why your, let's say for example, your concentration is so far off from the accepted concentration, going back to the example of accurate versus precision. So a random error is one type of error that can occur, and these are measurements that may be either too high or too low. These could be caused by just procedural ineptness, but it's something that you are not aware of that you did. It could be something hypothetical that you could then go back and see why, and how is it that we determine what could have happened. This is when you're able to statistically look at your data. So you look at the statistics to see where that random error might have occurred. The reason why is because you're always assuming that you're doing multiple trials. And so with anything, obviously, yes, we are human and we will make some errors. But the more trials you do, what you're doing is decreasing your level then of a chance for something to happen, or you're trying to be as accurate as possible. So statistically, by having multiple trials, you're lowering your uncertainness, okay? And this also deals with your uncertain digit when measuring. You're accounting for then that people may be reading your last digit differently because of rounding. But again, by maybe averaging the whole class together, it will make better results. So random errors, specific example would be maybe for one, you might have forgotten to tare maybe your balance, and so it messed one up, but you're able to see that, and it's blatantly obvious then in your data how one is very, really low, or another is really, really high, so way off from your others. Systematic errors, though, are measurements that are always skewed in one direction, and these are very difficult to determine statistically. So systematic errors are very hard to be able to catch. These are caused by poor measurement calibration, meaning if, let's say, for example, you forgot to tare it once, that would be a random error. But if every time you took a weight or measured the weight of something, the mass of something, and it was always not tared, well, that's going to increase all of your measurements, and that would be a systematic error. If you balanced improperly, again, not forgetting to zero or tare your scale, or also too, if your thermometer is improperly marked, that is going to influence all of your temperatures either being too high or too low. So again, no matter what, no matter how many times you go through and do it, you're probably going to end up with the same results because of those errors. And it's very hard to catch those. It's a little bit easier with random. So what we just went through is random error and systematic error. You're going to want to use these and reference these, especially when we do the Intro to Measurement Lab. And then become very good at using these to explain why you have error in your lab, and you're always going to explain this in your error analysis in your conclusion. Never ever again will you say human error, okay? And then we also talked about accuracy versus precision. Again, this would be very good terminology to use whenever you do error analysis. And make sure that you're able to provide examples of the two when it comes time for your test.